So I don't know if you recognize, but there was back in the day, the definition of the derivative says that the limit as h approaches 0 of f of x plus h minus f of x all over h is the derivative. Now, I don't need to do derivatives like this anymore. If I can identify what is my f of x, I can use my derivative rules to find the derivative. And what is the x I'm plugging in? Well, if you look, our function is the cosine. So let's write that down. F of x is the cosine of x. I want to find the derivative at this particular x value. So it's the derivative at pi over 2. It's as simple as that. I don't have to do anything crazy anymore. I don't have to do that limit ever again. But if I don't know that's the derivative kind of in plain sight, I'm not going to be able to do it. So it's important that you understand that that is just saying find the derivative, so do it. What do we know the derivative of a cosine is equal to? It is equal to negative sine. So we're really just taking the derivative, getting negative sine, and plugging in pi over 2. Well, the derivative is negative sine. The sine of pi over 2 is 1, so the negative in front makes the answer negative 1. So don't do that limit ever again. Recognize that it is the derivative, pull out the function, do its derivative, the shortcut method, and then just plug in whatever a value they happen to be using. In this particular case, pi over 2. So again, it's just, this is the derivative. What's our function? Cosine. What are we plugging in? That's the things right here. In this case, pi over 2. The derivative of that is negative sine. Plug in pi over 2, get negative 1. You're done. Because doing a limit with a cosine like that is very, very difficult. Okay. So I just wanted to give you a hint of some problems that you could possibly see when we take a semester exam. Yes. Yeah, don't do that. Okay. So we are going to be talking about the chain rule, which I think you will appreciate. It's basically going to help us to learn to differentiate composite functions, so even more complicated functions than what we've seen so far. So up to this point, if I asked you to find the derivative of this, there is no way to do it. You don't know. This x squared plus 1 is captured in a square root. Yes, it might be helpful to write that as a 1/2 power instead, but then what? What's the rule? What do we do? So that's where the chain rule comes into play. It's a brand new rule we have to memorize and know. And here it is. If we have a composite function, so first let me show you this. If we have a composite function, so f of g of x, so g is captured inside of f, you are going to take the derivative of the outer function, leave the stuff there, then multiply it by the derivative of the inside stuff. Okay, so it's another one I have a silly kind of little talk through. Okay, so you take the derivative of the outside stuff, you leave the inside stuff there, and then you take the derivative of the inside. That should say the word inside. Okay, so let me say it again. We have this composite function. G of x is our inside. We take the derivative of the outside stuff like we can, whatever it is, whether the outside is a square root, whether the outside is a trig function. And then if it has junk inside, we just leave the junk there, and then we multiply by the derivative of the junk. So take the derivative of the outside, leave the inside stuff there, take the derivative of the inside stuff, and you're going to multiply that by whatever you got initially, okay? So take the derivative of the outside stuff, leave that stuff exactly alone inside of it. Then take the derivative of the inside stuff and multiply it by what you have, okay? So that's our rule as far as how composite functions work. We work our way from the outside inside. It's kind of the opposite of what we do normally for a composite function. So we have to really identify what's on the inside and what's on the outside, okay? So it's super important that we recognize what's our inside stuff, what's our outside stuff, okay? So we're going to take now a moment and we're going to go back to that original question, that what is the derivative of the square root of x squared plus 1? So let's go back to this question, and now for the first time, we should know how to do that, okay? So the first thing we want to identify is what's stuck on the inside, x squared plus 1. What's on the outside, a square root. Any rewrites that we would do from before, we want to do now. So our f of x function is x squared plus 1 to the 1/2. So any rewrites we would do before, it's going to be a rewrite you want to do initially. Okay. Now, how do we take the derivative of that? Well, we're going to take the outside function, which is a power function, a power to the 1/2. We're going to drop the power down in front. Power goes down by 1. But our stuff just stays there. Okay, so we use the power rule. Let me show you again. The power drops down in front. Power goes down by 1. Stuff stays there. But then we're going to multiply by the derivative of that inside stuff. The derivative of x squared is 2x plus 0, or 2x. That's your answer. Do I care about a simplification at this point? Not in the least. First step, all we need to do is practice that first step. Okay, so let me talk through again. If you have something on the inside that is stuck, you're going to evaluate the outside function like normal. That's a power function. Power drops down in front. Power goes down by 1. Stuff stays there. Then we're going to multiply by the derivative of the inside stuff. That's the chain rule. Now, if this stuff had another layer of stuff stuck in it, we would do it again and again and again until the derivative is just a clear one-term thing, okay? So let's practice. So I'm going to write down A. And B, and I'm going to show you the distinct difference between the two of them. Those are very different problems. A, it is very clear that our inside stuff is x squared. Our outside stuff is sine, okay? So the derivative of this one's pretty straightforward. You take the derivative of the outside stuff. The derivative of a sine is a cosine. Leave the stuff there. Multiply by the derivative of the inside. What is the derivative of x squared? 2x. So we're going to multiply by 2x. That's it. Now here's the problem with B. The notation for a power on a sine, cosine, a trig function is deceptive. Mathematicians love to write things in a shortcut way. But they do that, and then sometimes it can look funkier and look like it means something different. Anytime you see this notation for B, you have to do a rewrite. This is our rewrite. This is the same as the sine of x, the whole thing squared. So always do that rewrite when you see a power next to your trig function. That means that trig function should be in parentheses and squared. It's just mathematicians are lazy about what they're writing down. You know, back in the day, think about when math was first, you know, really becoming a thing in Newton's day or whatever. They're writing all this stuff by hand. And so if they could write it in a shortcut manner, they're going to do that, okay? So this notation means this. You need to know it means that, and you need to rewrite it every single time before you get started. Now we can see what is our inside function. Sine of x. What is our outside function? The power, the square. So now it is the exact kind of opposite thinking of A. They're almost identically flip-flop problems. So our outside function is the square. We do what we know about the power rule. Power goes down in front, power goes down by 1, so that's the first power. The stuff stays there. But now don't forget to multiply by the derivative of the stuff. What is the derivative of the stuff that's sitting there? So it's just cosine. Remember, sine is positive. The only ones that are negative are our cofunctions. Cosine has a negative derivative. Cosecant has a negative derivative. Cotangent has a negative derivative. So that's it. That's the difference between those two. It's notation. So be very careful and mindful of what the notation is really telling you as to what's on the inside and what's on the outside. Okay? Okay. Now, Leibniz notation is sometimes used for this stuff. See this du dx? That means that's the derivative of the stuff inside. A power rule always, if there's a power on the outside, is always going to work the same. If I have a power to some stuff that's a complicated piece of stuff, you drop the power down in front, power goes down by 1, leave the stuff there, and then take the derivative of the stuff. So it's just, they are specifically showing you every time what happens to a power of a function. So if we have a power of a function, drop the power down in front, leave the function there. Power goes down by 1, but don't forget to take the derivative of the inside function. Okay, so we've got stuff to a power. Power drops down in front, power goes down by 1, leave the stuff there, but don't forget to multiply by the derivative of the stuff. My very mathematical language there. What's the stuff inside? Do the outside stuff, leave the stuff there, multiply by the derivative of the stuff. Okay. So that's super important as we go through this process. That's just the power rule. That's how a chain rule happens for a power. Always same thing. Power drops down in front, stuff stays there, power goes down by 1, multiply by the derivative of the stuff. You just have to know that rule. Okay. So even if we have something to the 100th power, up to this point, there's no way to do that. Up to this point, we would have to take x cubed minus 1, multiply it, and distribute it out and FOIL it 100 times. That's impossible. I mean, it's pretty much impossible. Think about how many terms you would have. I mean, no. Okay? So instead, we get to use our power rule. It's a chain rule. What's the stuff inside? X cubed minus 1. What's our outside? So here's our inside. Here's our outside. So the derivative of that, drop the power down in front, leave the stuff there. Power goes down by 1. Multiply by the derivative of the stuff. Well, the derivative of x cubed minus 1 is 3x squared minus 0. And if you put the 0 there, it's okay. Go for it. Look at how much easier it is because we have the chain rule. The chain rule becomes super essential for these functions that either are complicated, high-powered functions like this, or maybe a sign that contains a polynomial or something like that. Okay. Let's do another one. Many functions require a rewrite. This function, right now, the way that it sits, you would have to use the quotient rule, which is, anytime I see a constant in our numerator, that tells me I can do a rewrite to make my life easier. So I would rewrite this function as x squared plus x plus 1 to the negative 1/3. Now let's everybody contemplate why that happened. The negative appeared because we were in the denominator. That's going to flip that to our numerator. The 1/3 is representative of a cube root. Okay, so hopefully that part doesn't surprise you. This is our inside function. This is our outside function. Okay, so let's take our derivative. The outside function is a power rule. So the power drops down in front. The power goes down by 1. Negative 1/3 minus 1 is negative 1/3 minus 3/3, or negative 4/3. Stuff stays there. The stuff stays along for the ride, but I must multiply by the derivative of the stuff. The derivative of x squared plus x plus 1 is 2x plus 1. That's how you find the derivative of a composition function. Okay, so let me go over the rule one more time. This is a power function, so we know that the power goes down in front, power goes down by 1, the stuff stays there. No, I was just showing, that's okay. And then we multiply by the derivative of the stuff. Okay. So just be careful. It is up to you to recognize when the chain rule is necessary. There are some problems where you can use a chain rule, but you can sometimes avoid it if you don't want to, if you actually can multiply through. So say you have two polynomials. If you distribute through, you won't have to use it, but you can. You have an option now. Okay. So here is a function where we have a function trapped inside of a 9th power. We would not want to take that fraction to the 9th power. It would be absolutely disgusting. I'm going to show you two ways to do this problem because I find some people like the one way and some people don't. So I'm going to show you both ways. We're going to show you two methods. So I'll call this method 1. Okay. In that method, following the chain rule, we have a fraction stuck inside of a 9th power. So our outside function is the 9. Our inside function is the fraction. So our derivative, we're going to drop the 9 down in front. Power is going to go down by 1. The stuff stays there. And then we're going to multiply by the derivative of the stuff. Well, what is the derivative of a fraction? We have to use the quotient rule, right? Okay. So let's do the quotient rule for this, okay? So it's bottom times the derivative of the top. The derivative of the top is 1, so I'm not going to even write it. Well, I'll write it with that. Minus the bottom. No, I'm sorry. Bottom times derivative of the top minus top times the derivative of the bottom all over the bottom square. So that is a perfectly acceptable method. Go for it. Yay, that's your derivative. Wonderful, fabulous, great. Okay. But I want to show you a slightly different method that some students have liked in the past. If you do a rewrite, you can make that t minus 2 to the ninth times 2t plus 1 to the negative 9. And then you can use the product rule. Okay, so you can do it like that. All I've done is separated kind of our numerator and denominator. I made my numerator to the ninth power. I made my denominator to the negative ninth power. So that's an option. Feel free at any time, if there's a denominator, you can always write it to a negative exponent. And then you avoid the quotient rule, you get a product rule instead. I don't know. Let's do the derivative looking like this. So now we get a product rule. So it's first times the derivative of the second. Now, the second is a chain rule because it has a 2t plus 1 stuck in a power. So we're going to drop the negative 9 down in front. Stuff stays there. Power goes down by 1. Don't forget the derivative of the inside. Plus. Now, that was first times derivative of the second. Now, it's going to be second times the derivative of the first. The derivative of the first, we're going to drop the 9. Power goes down by 1. Don't forget to multiply by the derivative of the inside. In this case, the derivative of the inside is just 1. So both methods, if we were to simplify, which I'm not going to, but if we were, both of those things are equivalent. So both will get you the same direction. You can avoid quotient rules by making your denominator a negative exponent. But don't forget, if it has something inside of it, you must do the chain rule. So both of those methods work. If and when we take a quiz over this stuff, if one of you decides to do method 1 and one of you decides to do method 2, you're both correct. So there are many ways to get to our derivative. Any questions about example 5? Okay. Let's look at example 6. Now, you will see that it is a product. So let's put a little dot there to remind us that we have to use the product rule. Both pieces are complicated because of the fact that we have an inside polynomial and an outside power. So let's do our derivative. So it's going to be first, leave it alone, times the derivative of the second. Now, to take the derivative of that polynomial, it's a power chain. You're going to drop the 4 down in front. Stuff stays. Power goes down by 1. Don't forget to multiply by the derivative of the inside. Make it in parentheses. So that would be 3x squared minus 1. Okay. Plus the second, just write it in parentheses, times the derivative of the first. Now, the first piece also is a power chain rule. Drop the 5 down in front. Leave the stuff. Power goes down by 1 times the derivative of the inside stuff. The derivative of 2x plus 1 is 2. Now, at this point, I do not care about simplification, but I want to talk about simplification because it will become something we have to do eventually. So if we look, this is actually term 1. This is term 2. They will always have something in common. See how these ones have a 2x plus 1 in common? That lowest power, 2x plus 1 to the 4th, can come out. Then if you look at the two terms again, they should have this in common. They do. The lowest power is a 4, so we can take out 4 of those. Or the lowest power is 3. We can take out 3 of those. And then here's what I found. So we have, so let's show what we've taken out. Okay, so we've taken out 3 of those. We're left with 1. We've taken out 4 of those. We're left with 1. Now, if you look at the pieces that I have not highlighted, they do have a 2 in common. So let's take out a 2. Okay. Now, again, you don't have to do this yet, but I want to prepare you. It is coming. Okay. So from our first term, I've taken out all of that. This became a 2. I have one of these left because I took out 4 of them. I have that left. So I'd be left with a 2, 2x plus 1, and a 3x squared minus 1. Okay, let's analyze this junk. I took out all of those. I took out the 2. I have a 5 and one of those. And then, if I was really ambitious, I would leave this. You always leave those pieces. But I would probably multiply that and get it simplified down. But I'm not going to for that. But this pattern, it happens in some applications. We will have to eventually do something with it. Okay. Okay. Let's do another one. Now, this is a triple chain. The innermost function is a tangent, which is stuck in a cosine. The cosine of the tangent is stuck in the sine. So we're going to do it in layers, okay? Okay. So how do we take the derivative? Well, you have to start with the outside, work your way to the inside. So our outermost function is a sine, which becomes a cosine of that stuff, which is the cosine of the tangent. Okay. But we have to multiply by the derivative of that stuff. What stuff am I talking about? Cosine tangent. Now, if I just gave you a problem that said, what is the derivative of a cosine tangent? You would say, oh, that is a negative sine of the stuff times the derivative of the stuff. What's the stuff now? Tangent. What is the derivative of a tangent? Secant squared. So that is the derivative we're searching for. Okay, let's go through that process one more time. The outermost function is a sine. It becomes a cosine. Leave the stuff there. But then ask yourself, what is the derivative of cosine tangent? Well, the derivative of a cosine becomes a negative sine. Leave the stuff there. But what's the derivative of a tangent? Secant squared. It's weird and gross. When you have more layers, you just keep working until you've come up with, because what is the derivative of x? That inside stuff is 1. So now you know you're done. There's nothing to go further. So when you've got this to a nice derivative, you're done. Okay. Does that make sense how I worked through that kind of? Okay. So your assignment is in the book, section 2.5. Again, the odds, you'll be able to check your work. Those are the problems that you need to give a try. You have some time now. Why don't you work on those right now? There you go.